All right, today we are diving headfirst into a real mind bender, something straight out of the quantum realm. Physicists have just managed to prove a paradox in the lab that basically throws our everyday common sense right out the window. It really pushes the edge of what we even thought was real.
Okay, so get this. At the very heart of this whole thing is a flat-out contradiction. You've got a situation where our normal classical logic says an event has a 0% chance of happening. It is completely impossible. But quantum theory looks at the exact same event and says, nope, that's not just possible, it's basically a sure thing. And the craziest part? They just proved it actually happens.
So, how on earth is that possible, right? Well, the answer is tangled up in this really fundamental, but let's be honest, deeply weird rule that governs the entire quantum world. It's this concept called quantum contextuality. See, in our big, everyday world, things have properties that are just there. A ball is red whether you're looking at its shape or measuring its weight. But down in the quantum realm, it just doesn't work that way. A particle's property, like its spin, doesn't really have a fixed state until you measure it. And here's the kicker. The answer you get depends entirely on what other properties you're measuring at the exact same time.
A good way to think about it is with the word set. By itself, what does it mean? Not much. But put it in a sentence, a set of dishes, set a new record, the sun will set, and suddenly the context gives it a specific meaning. A quantum property is a lot like that. Its value is only defined by the measurements happening around it.
And this isn't just some weird philosophical quirk. This weirdness is actually the whole point. Scientists think this very contextuality could be a ridiculously powerful resource. It might just be the secret sauce, the magic, that could finally unlock the incredible potential of quantum computers.
So this strange rule really set the stage for what these scientists wanted to do. They weren't just trying to prove contextuality was real. We kind of knew that. No, they wanted to find the absolute purest, most powerful, and most efficient example of this quantum paradox that anyone had ever dreamed of.
So, how do you go about hunting for a paradox? Well, you get clever. You turn it into a math problem. The researchers basically translated all the relationships between these quantum measurements into a kind of network, a mathematical graph. Then the hunt was on for the simplest, most perfect graph that had the exact properties they needed. That graph would be their blueprint for everything. And this whole search centered on a question that has had physicists scratching their heads for more than 30 years. To pull off this kind of perfect black and white paradox, what's the absolute bare minimum number of measurement contexts or different setups that you need? The answer, it turns out, is just 3. Now, for years, the best anyone could do was 4 measurement contexts. So by proving the minimum is actually 3, this team didn't just break a record. They found a whole new, much more powerful version of this quantum weirdness. Now they just had to find the exact blueprint for it. And they found it. The blueprint they uncovered is this really elegant, beautiful mathematical structure called the Perkel graph. It's the unique, supersymmetric design of this graph that perfectly lines up all the measurements, holding the secret to creating the biggest possible clash between classical and quantum rules. This is a massive leap forward. I mean, look at this. Before, you needed at least 4 contexts. Now it's just 3. That efficiency jump creates a way stronger effect, a violation ratio of 3 to 2, which is the biggest you can theoretically get. They didn't just find another paradox. They found the most potent one possible. But, having the perfect blueprint is one thing. Actually building a machine that can follow those instructions, well, that's a whole other ballgame, a massive challenge. And the challenge here was just immense. To actually bring this Perkel graph to life, the experiment needed to control and measure quantum states in a mind-boggling 37-dimensional space. I mean, try to wrap your head around that. It's like trying to juggle 37 different things at once with absolute perfect precision. It's way beyond what any normal quantum system can handle. Their solution was just brilliant, a custom-built processor that runs on light. First, they encoded all that complex 37-dimensional data onto perfectly timed pulses of light. Then, these little light pulses raced around a loop of fiber optic cable where they were processed. The real genius, though, was how their system broke that enormous 37D problem down into smaller, doable chunks. Finally, a supersensitive detector read the light pulses to get the final answer. Okay, so the theory was ready, the blueprint was found, and their light-powered machine was built and ready to go. It was finally time to run the experiment and ask reality the big question. Do you follow common sense, or do you follow the strange rules of quantum mechanics? The results were just stunning. The team's measurements lined up almost perfectly with all the quantum predictions. And for that one key event, the one that classical logic says is impossible, a 0% chance, the experiment saw it happening 99.83% of the time. It was about as close to a perfect confirmation as you can get. Reality really is this strange. So this was really a 2-for-1 success. Not only did the experiment prove this incredibly powerful new paradox was real, it also proved that their innovative machine worked like a charm. This light-based processor is now a new tool that opens up all kinds of doors for exploring other bizarre quantum effects in really complex systems. So what's the big takeaway here? Why does all this matter? Well, they found the most powerful and efficient proof of quantum contextuality that we know of. They created a brand new, scalable way to do these super high-dimensional experiments. And by doing that, they've shined a light on a new path for finding the very things we need to power quantum computers and maybe even solve other deep mysteries about our universe. And that just leaves us with this final thought. This experiment proves, pretty definitively, that the universe plays by rules that are profoundly alien to us. And it really makes you wonder, what other impossible things, what other rules that we take for granted are just sitting there, waiting for us to figure out the right way to ask the question?